Hello everyone. In this first lecture I will talk about the basic underlying ideas underlying machine learning, and I will also introduce most of the terminology that we will use throughout the course. So the first and most important aspect or part of machine learning is data. So it's all about data, and so what you see here is an example of what we call a data set. Right? So this data set here consists of 10 images of skin lesions, okay? And so each image we would refer to as an instance in the data set, or as an example, or as a data point. And in this case, our data set is labeled. So each of these examples here, each of these images, has a certain label assigned to it. So we say it's annotated, and in this case it's annotated by expert dermatologists, right? And so they annotated each of these images as being benign, so nothing to worry about, or malignant, so cancer. And so let's say that the top 5 here were annotated as malignant, and we have the benign ones here at the bottom, right? Okay. So that's the data set. Now, the other important aspect is features. So we're going to work with feature vectors. So now let's say that we have a job here to make some kind of a model, make a system, make a computer program that can look at one such an image, and it can actually predict whether this is whether this is a benign or a malignant skin lesion. So it's going to actually try to predict what the dermatologist is going to, what the diagnosis is going to be of the dermatologist. So if you want to automate this in some way, what you need is, of course, some way to represent your image in a mathematical way, right? And we will do that by defining features of the image, right? And once we have done that, so we put the whole task in a mathematical formulation, we can then apply mathematics to get classifiers. In our case, we will be mainly looking at classification models. So they take feature vectors as input, and they will output a prediction, in our case a diagnosis, right? And so next to dataset, another very important aspect is the feature extraction. Right? So for each image we will compute a certain property or a certain attribute of that image, which would help the classifier here to make the correct diagnosis. So now if you look at how dermatologists do this, I mean, they are experts in this field, but they use a very similar approach. So they also have a number, and I'm showing very simple ones here. They have much more complicated ones, but these are the ones that we ourselves can see as well. So for instance, here the asymmetry is just some value that would tell you how asymmetrical a certain lesion is, right? And the same for the border, same for the color, same for the diameter. So each of these features, each of these properties will have a certain value for a certain image, okay? So let's say we don't have just 10 images in our dataset, but we have like 200 of them. So 100 labeled as benign and 100 labeled as malignant. Then we can look at, like I said, a certain feature of these images. Let's say in this case we look at the eccentricity. So eccentricity is actually a value that tells you to what extent a certain shape deviates from the circular shape. So high values is less circular shape, low values is very circular shape, okay? And so we can, for each of our 200 images, we can compute this value for this feature, and then we can plot these values as a histogram, or as in this case, as a density plot, okay? And so I created 2 of them, so one for each of the classes. So here we have the orange class, which is the malignant images. We will also refer to this as the positive class. And we have all the images labeled as being benign. In the blue class here, which we will refer to as the negative class, okay? And so what you can already see here is that this feature here provides already some separation between our 2 classes. It tells you something about it being malignant or being benign. And so this would be a very good feature for machine learning. So That brings us to another topic, which is actually the model itself, right? So like I said, we can use this feature to perform a certain diagnosis. So we can clearly see that if this feature has a very high value, so a non-circular shape of the lesion, it's very likely to be a malignant image or a malignant skin lesion. While if it's very circular, it's very unlikely to be a malignant lesion. Okay, and so if we put some threshold here, like the dotted line here, right? Okay, and we can, so we have a value t here, t, which would be 1 in this case, then this threshold here actually performs classification, right? So very simple. If the value of eccentricity for any image is higher than 1, larger than 1, then we will diagnose that image as being malignant. Okay. If it is smaller than 1, we will diagnose it as being benign. So that will be our prediction. So we made the classification already, which means that this t that we have here, this dashed line, is a machine learning model which we have fitted based on the data. To make this more clear, what's happening is that if our value of t, our threshold, is bigger than 1, right, we would end up with this situation here. And so any value of the eccentricity here bigger than 1 will result in a diagnosis of the positive class, in this case the malignant lesion. Okay, and so the same here, if it is smaller than 1, everything here will be diagnosed as being benign. Okay, so now we put this threshold here at 1. Visually that looked pretty much okay, but there is no clear reason yet why we would have chosen to do that. So I could have chosen also to make it a bit smaller here, put it at 0.7, and as you can see, that has some serious consequences for the predictions, right? So in this case, I'm actually trying to avoid making a bad call on it being malignant. So I want to avoid that if the skin lesion is indeed malignant, that I would classify it as benign. So I would consider that to be a very bad error, right? So to diagnose somebody who has cancer as being healthy, okay? And so of course you can see that the consequence of that is that there will be slightly more healthy people, healthy skin lesions, so benign skin lesions, that will be classified as being cancerous, as being malignant, right? And so depending on where you put this threshold will have different consequences. And so before you decide on where the thresholds should be, we have to decide on what is important for these predictions, which consequences are we willing to accept and which are we not willing to accept. Okay. So that brings us to evaluation. Okay. So evaluation, another very important aspect of machine learning, right? And so for classification, which is what we are looking at here, a typical way to evaluate the predictions that are made is by making something called a continuity table or a confusion matrix. So basically what we're going to do is we're going to divide the predictions into 4 categories. Okay. So let's take this situation here. So this was our classifier again. Okay. And so what we see here is everything that is classified as positive. Right? So we said everything above 0.7 we're going to classify as malignant skin lesions, so the positive class. Okay, so that's in this table is this column here. So here we're looking at everything that is classified as being positive. Now of everything that's classified as being positive, we have 2 classes. Right? So we have the actual positive class, so they are correctly classified, so we call them true positives. And we have the falsely classified, right? So they are falsely classified as positive, but they're actually negative, right? So we call them false positive. Okay. And so similarly, for everything that is predicted as negative, which we have here, we would again have 2 classes, right? And so we would count the number of negatives here as being true negatives because they are classified correctly. And then we have some of them which are actually positive and they're classified as negative, so we call them these false negatives. So this way we have counted the true positives, the false positives, the true negatives and the false negatives. Okay, and so given these values that we have here, we can now compute a whole bunch of evaluation metrics, right? And so again, which metric to use depends on the consequences of your prediction. But of course, there are some metrics that are used much more often than other ones, and I guess the most well-known metric is the simple accuracy metric, right? And so accuracy is just looking at everything that is predicted, so that's the true positives, the false positives, the true negatives, and the false negatives. How many of those were predicted correctly? So that would be the true positives and the true negatives, right? And so given these four values, we now computed the accuracy metric. But of course we can compute many other metrics, and ones that we will be using throughout the course and also in the projects is the true positive rate and the false positive rate. So the true positive rate just looks at everything that is positive. So that would be the true positives, but also the false negatives, right? Because they're positive, but they were falsely classified as negative. So of everything that is positive, how many of those are actually truly positive? Right, so that's the true positive rate. The false positive rate looks at everything that is negative, so these would be the false positives and the true negatives, and it sees of those how many were falsely predicted as positive, so the false positives. Right, so we have true positive rate and the false positive rate. Now we can compute this true positive rate and false positive rate for different values of our threshold. So let's go back here. Okay, so we have here a threshold at 0.7, but we can put it at 0, we can put it at -1, we can put it at 2, at 3, and so on. Right? And so for each of those choices, we will of course have different values for our true positives and false negatives and true negatives. Okay, and so if we have different values here, we will have different values for the true positive rate and the false positive rate. And so if we range our value of t, we give it several values, we can compute for each of those the true positive rate and the false positive rate, and then we can plot these against each other, which is what's happening here. So here we have the false positive rate, the true positive rate, and here we have the result of different values for our classification threshold t. So let's now consider two very bad classifiers, two very bad classification models. So the first one would be a model that, given an image, it would always predict it to be malignant. So it would always assign the positive class to an image, so to any image. So that would be a very bad model, very bad classification model. Now, the true positive rate, since the malignant images are true or positive, the true positive rate will be 1. But of course the false positive rate will be 1 as well. So we would end up here somewhere. This would be a very bad classifier. So the other very bad classifier would be one that predicts benign. So it diagnoses every image as benign. Again, a very bad classifier. Now in this case we would have a 0 true positive rate, and we would also have 0 false positive rate. So we would end up here, right? And so this line here, this dashed line, actually represents all the very bad classifiers. So this is not what you want. What you want is this classifier that has, of course, a 1 true positive rate, and of course a 0 false positive rate. So that's the one you want to have here. Okay, and so you can see that this curve that we have here, which we call the receiver operating characteristic curve, right? This actually represents how well your classifier is performing independent of your threshold value t, right? And so we want, of course, these values to be as close as possible to this 1, 0 here, okay? And so one way to summarize this curve here, right, into one value is by taking the area under the curve. So how big is the area under the curve? The bigger it is, the better the more accurate the predictions were. Okay, and so we call that the area under the curve. And so this is also what you will be using throughout the projects in the course. So now we looked at this one feature, right, and we computed the values of that feature for each of the images in our data set. Now this is not a bad separation, but it's not perfect, right? So the classifier using this feature is always going to make errors. So can we improve? Well, one thing we could do is we could see whether we can find another feature that's maybe performing better. Let's say that we cannot find such a feature. Let's say that the next best feature that we find is this solidity feature. Right? So again, it tells you something about the legion itself, and we can compute the solidity value for each of the images in our dataset, and we can plot these histograms again, just like we did with the eccentricity, and we can see again some separation, not as good as eccentricity, but again, this is a valuable feature for the diagnosis. Okay. Now, what we can do also is make use of both of these features, right? So now what I've done is I've plotted one feature here, the other one here, and so each point you see here is a data point in the dataset. So it's an example, and it is represented by these two features, right? So a vector of these two features, which we call a feature vector. Okay, and so I labeled them by class. So again, the positive class orange malignant, and now we have blue benign. Okay, and now we can again build a classification model, but this time this classification model can make use of these two features together, right? And so you could think of this like the image here on the left. So this is the exact same data set. Okay, and so now we have fitted a model like this. So we have a linear separation here between the orange and the positive class, the blue, the negative class. Okay, so this is very similar to this threshold T that we defined previously, but now the threshold is actually dependent on two features. Okay, and so again, just like with the one feature, we have generalization. We say, okay, everything that is on this side of this separation, the decision boundary as we call it, right? Everything here will be classified as positive. Everything in the blue region here, every point here will be classified as negative. So you can see that we actually use this data set to fit this threshold here, to fit this decision boundary, and at the same time we generalized the data set, because now for each image we can make a diagnosis. So for instance, we could have an image somewhere here, which was not in our data set, but given the model we will predict this image as being benign based on the values of these two features here. Okay, so this is what machine learning is all about. Now you might say, why choose this decision boundary? Why not go for something more complex like this? And as you can see, this decision boundary has classifies 97% of our data points correctly. In this case, it's more complex. It can do 99% correct. So I would consider this to be a better model because it has better performance on our data. And so that's what we will be talking about in the next lectures, that is not always the case. And this trade-off between complexity and what we will see as being fitting the noise, overfitting, is a huge part of machine learning, and it's going to be one of the main things you will be doing throughout this course. So one final aspect or important aspect in machine learning is the pre-processing of the data. So to prepare your data for fitting with machine learning algorithms. So one important aspect here is the scale of the features, right? And so the eccentricity and solidity values that we used in this lecture have been scaled before, but let's say that they were not. So let's say that this eccentricity value actually has a value between 0 and 100 throughout the data, and the solidity feature has a value between -5 and 7. Okay, so you can see that these have clearly different scales. The range for eccentricity is much higher compared to that of solidity. And so from a mathematical point of view, this might cause issues when fitting machine learning models. So it's a very good practice before doing any fitting to make sure that your features have been properly scaled or normalized. Okay, and so one way to do that is through standardization. So what you would do is you compute the mean and the standard deviation for a feature. So x is a feature here, and so for each of the values of this feature we subtract the mean and we divide by the standard deviation to make sure that the mean of the feature is going to be 0 and the standard deviation is going to be 1. So that's one way to do this. Another way to do this is by min-max scaling, where you make sure that all the features have the same range. So let's say between 0 and 1. Yes. And so one way to do this is to take the feature, compute the minimum and the maximum values, and then subtract for each value of this feature the minimum value and divide by the maximum subtracted by the minimum. Okay, and so both of these will make sure that features are scaled similarly. This one will sort of also change the shape of the distribution, while this method will leave that shape intact. And so it depends on the problem that you are dealing with. One of these two will be the better performing one. So here's an example. A typical example where this is required is, of course, microarray measurement, gene expression measurements. Here you can see an unprocessed dataset. So we have a number of genes. Each gene can be seen as a feature. Okay. And so we have the values of this feature in our dataset represented by box plots. Okay, and you can see that they are on different scales, and they are also not centered very well. So if we apply standardization, we would end up in a situation like this, where they end up on a very similar scale, and they're centered quite well. Now what you see here in the box plot is the median. So the green line here represents the median. And so that's why they aren't centered exactly on 0, because we actually centered them on the mean. Okay. And so this is the result of min-max scaling. So now each feature have a value between 0 and 1, and also the individual box plots, the shape of the box plots is still intact. So then a quick note on the course itself. So as you have seen, this is actually a collection of Jupyter notebooks. So with interactive Python code in there, which you can run and even change and see what happens. And so the main packages we will be using is pandas. So pandas will allow us to work with the data itself, manipulate the data. And so you will learn all about pandas in the Kaggle Learn project that I wanted you to do. And we will also make use of scikit-learn, which is the main package that implements all the machine learning methodology that we will be using throughout this course. So just to show you how simple things actually are, so you will learn about pandas. And so pandas has methods, in this case read CSV, which you can use to read your data files and put them in what pandas calls a data frame. Okay, and so the data frame has a whole kind of methods, utilities that can be used to manipulate this data. A very simple one here is to, for instance, just show the 5 first rows of the data set, or here to use the shape property here to look at how many rows and how many columns there are in the data set. So you will learn all about that in the Kaggle Learn exercise. The other exercise I wanted you to do is the data visualization part, which will teach you all about this Seaborn package here. And Seaborn will allow you to very easily, in just a few lines of code, to make these kind of plots that we made for this lecture. Okay, so this is an example for the density plots. This is a one line of code to make a nice scatter plot like this. So you will learn all about that in again in the Kaggle Learn exercises. And then finally, this will be the main workhorse, scikit-learn. We will come back to this in detail, don't worry. But just to show you again how easy it is. So you have seen decision tree classifier, so that's why I'm using it as an example here. So this is actually the way to build a decision tree from a certain dataset. So the dataset would be X, which would be the feature vectors, and Y would be the labels. And so all we do is we define a model, which in this case is going to be a decision tree classifier, which has some properties. In this case, the maximum depth of our decision tree is set to 5. And as you will see on the website, scikit-learn, there's a whole lot of other properties that can be set. So once we set that this model is a decision tree classifier, all we need to do is call the method fit to actually fit the model. And then we have our model, right? And so then we can make use of some other methods here, predict, to make predictions for feature vectors. So here we have loaded data, We have fitted a model and we use the model to make predictions in just a few lines of code.